good, but it's like great. I like I said, it's like.
Yes, I'm so mad.
Okay, so you guys picked up the quiz review. This is for you to keep, so you can write on this. This is yours. So we can write on keys now.
Yeah.
So today and tomorrow, we're going to be working through the quiz review. Friday and Monday, we're going to start the next unit, but we'll still have the second or the latter half of class to continue reviewing for your quiz, and your quiz will be next Tuesday. The formulas that you need to know, okay, I'll leave this up on the board until Tuesday. Pythagorean theorem, area of a rectangle, area of a square, area of a triangle, area of a circle, and circumference of a circle. Okay. Everything else, all the other shape formulas, I'll give you.
Next week, it's review.
Say it again?
We 4 days to review.
Well, yeah, we have 2 days to review, and then Friday and Monday, we do need to start the next unit, but we can still have the second half of class to continue doing practice problems. Right, before I forget, so make sure that when the bell rings that you guys are going to advisements in 4402, or is it 20? What's the ref? 2204, sorry, 2204. And if you have, if you need a pass to go to, media center, or you have a pass, if you guys can still go to Miss Mormon because she's the one taking attendance during advisement period. So go through her so that she can keep track of attendance. Let's see. Okay. Let me just briefly go over page 22. So number 2, we're just building the derivative equations here. So a equals pi r squared becomes 2 pi r dr dt. Circumference is dc dt equals 2 pi dr dt. We have the information provided here. So let me just, let's see if I can work through this one so you guys can see all the steps. Okay, I just want to get the derivative out of the way in case I need it. So dA dt equals 2 pi r dr dt. Circumference is 2 pi r. dc dt is equal to 2 pi dr dt. The area of a circle is increasing at a rate of 1 square centimeters per second. So I know that's my dA dt. How fast is the diameter changing? I would say let's just focus on the radius changing, because radius and diameter are they're half of each other. So if we can just figure out dr dt, we just have to double it at the end to get to the diameter. So let's just focus on the radius dr dt, and the circumference is 2 centimeters. So if I want to get to dr dt, and I'm given dA dt, I'm just trying to work my way down with this equation. Now my circumference is 2, and that's going to be my link towards finding my radius. So since my circumference is 2, and I also know that circumference is 2 pi r, if I set them equal to each other, and I get my sorry, my r, my radius is simply equal to 1 over pi. So I'm going to just take that and this and see if I can get down to my dr dt. So dA dt is 1. So 1 is equal to 2 pi r dr over dt. The pi's cancel out. I'm just left with 1 equals 2 dr dt. So 1/2 equals dr dt. So if 1/2 is the rate at which the radius is changing, then the diameter is simply double that. So my d over dt, the rate of change of the diameter, is simply 1 centimeters per second. I also want to talk about a Pythagorean theorem problem that is not a triangle so that we can kind of see some other variations. And we're also going to see some today as well. So we have an observer. He's standing 700 feet away from the launch pad. And the rocket launches off in this direction. So we have a triangle that's being formed. We know the observer and the base of the launch pad is never going to change. So that's going to stay at 700. But we know that the y is changing and z is changing. How fast is the observer to the rocket distance changing? So we're ultimately looking for dz dt. So we can just go ahead and, I mean, if you want to call this x, you can, but you just know that your dx dt is going to be 0. So either way, maybe if we want to do it that way, we can. X squared plus y squared equals z squared. But in this case, x is going to be the constant here. So x is 700. We know dx dt is 0, right? That this length is never changing. Y is 2,400 when the rocket is 2,400 feet from the ground. So that vertical distance. And then we're looking for dz over dt. The velocity is 900 feet per second. That's going to be the speed of the velocity. The speed of the rocket. So 900 feet per second. And then we're not told what z is, but how can we find z on our own? Yeah, Pythagorean theorem. A squared plus b squared equals c squared. We just use our calculator to get that value, and that value ends up being 2,500. And now we're just putting all this into the equation and just trying to solve for dz over dt. And that's how I got that 864 there. The x and dx dt, all this will just zero out. So really, it's just these variables we got to keep track of. So I think it's good that we talked about this because we're going to look at some other variations of Pythagorean theorem. And we just need to, we know it's always a triangle. We just have to kind of figure out, what's moving, what's not, and how is the shape changing as time passes. All right, so let's look at number 1 on your quiz review packet. Any questions here? Okay, we have a balloon rising vertically. Above a level straight road. at a constant rate of 1 feet per second. So here's our balloon rising. Just when the balloon is 65 feet above ground, a bicycle moves at a constant rate and passes right underneath it. So here's our triangle being formed once that bicycle passes underneath the balloon and it starts to go away from the balloon. The bicycle is moving at a constant rate of 17 feet per second. How fast is the distance between the bicycle and the balloon increasing 3 seconds later? So we know that this is a Pythagorean theorem problem, so x, y, and z. We'll just set everything up the same way as we've done before.
Mr. Yin,
Yes.
so the constant rate 17 feet per second,
Mm-hmm.
with the initial for x 17, or the initial for earning 17 times 3.
Yes, yeah. So let's talk about that. Let me label all the variables. We'll do the easy stuff first, and then we'll talk about the x and y. That's the x and y are a little bit more challenging here. Okay, dx dt, that's talking about the rate at which the bicycle is moving. What can we say that is? 17, yeah, 17 feet per second. And we know this is positive because it's causing the base of the triangle to increase. Okay, dy dt, 1, okay. Now, I do want to point out something about this diagram is the fact that when the balloon is 65 feet above ground, the bicycle is initially under the balloon. And after that moment in time, then the bicycle is going to move past and the balloon is going to continue rising. So this is going to be t equals 0. This is at time t equals 0. When the timer starts, this is where the balloon and bicycle are. And then after time passes, then bicycle will be here and balloon will be continuing to rise. Okay. So 3 seconds later, that's important, right? Because at t equals 0, this is where the balloon is. 3 seconds later, where's the balloon going to be? 60. Good. So it's going to 3 seconds pass. Each second that passes, it's going to keep rising up 1 feet per second. So after 3 seconds, the balloon is going to be at 68 feet. Does that make sense?
Yeah.
Okay. So at t equals 0, the bicycle is going to be right underneath the balloon. 3 seconds later, where's the bicycle going to be in relation to where it started? How far is it going to be?
17 times 3.
Good, 17 times 3. Yep. So at t equals 0, it's below the balloon. 1 second later, it will cover 17 feet, another 17 feet, another 17 feet. So 17 times 3. Yeah. Okay, so that's the hard part. The hard part is trying to figure out what these values are because time is going to pass and we have to figure out that length of the triangle on our own. Yes. Good. How do we get 68? So when the bicycle passes underneath the balloon is already at 65 feet above ground. But 3 seconds later, if it continues to rise at 1 feet per second, it's going to go 65 to 66, 67, and 68. Yeah, that's the hard part. The hard part is trying to figure out, oh, that balloon is going to change. The distance will rise up to 68 from 65. All right, are we comfortable with these values here? All right. Okay, how can I find z? Yeah, Pythagorean theorem. Okay, and then dc dt should be straightforward because all these will just get inserted into the equation, and you're just trying to solve for dc dt. what do you expect out of DZDT? Positive, yeah, because as the balloon is rising, as the bicycle gets further and further away, you expect the hypotenuse to also be increasing. All right, so try that. See if you can finish this problem on your own. And I do have the key attached a few pages later, so you can check your progress as well. Any questions with one? All right, number two. This is a linear approximation. So with linear approximation, remember your decimal is the last thing that you worry about. We don't worry about the decimal. Your focus is trying to build that tangent line equation. So use the x value to get your order pair from the function. Find the derivative using power rule. Plug the 2 into the derivative to get your slope. Get your point slope form. Y minus y sub 1 equals m times x minus x sub 1. And then once you have your equation, then you can plug that decimal into your equation. But start off by finding your order pair and your slope from your derivative. All right, so try those steps. You're just doing tangent line equation at the get-go. When you get your tangent line equation, just make a slight adjustment, get that y by itself, and that way you can just have your right side ready for that decimal to be plugged in. So most of linear approximation is just trying to get your tangent line equation, because your linear approximation is just literally one step. Just put that decimal in for x and you're done. Are we comfortable with getting that tangent line equation? Okay, order pair from the function, get your derivative using power rule, plug 2 into the derivative to get your slope, point slope form, get y by itself, and now we can put that decimal in. Okay, any question with part A? Part B should be even easier because the order pair slope is already given to you. You can jump directly into point slope form. Don't have to find the y value or the slope on your own.
Just like that with, the y of.
Yeah, just to indicate that I'm plugging 1.9 into my tangent line to get my above.
If you think we wrote it as an coordinate,
Uh, I think it's better to write it this way since this is how most of linear approximation problems are presented. So yeah, I'll write it this way. Since you have a calculator, see if you can get it all the way down to just a numeric answer. But without a calculator, you'll be able to leave your answer unsimplified. The step above it. All right, are we okay with number 2? All right, number 3, limits. So with limits, you're going to do direct substitution. See if you get a real number. If you get a real number, you stop. But if you get a 0 over 0, we now have a different method for handling 0 over 0. We're not going to go through factoring or conjugate method. We're just going to do derivative. So do the derivative of the numerator, do the derivative of the denominator, reevaluate, and see if that will get you to a real number. And that's L'Hopital's rule. Okay, but show me that you're getting that 0 over 0 before you commit to applying the derivative steps. So number 3, part A, there is no need for L'Hopital's rule because we already have a limit, so we can stop. Part B, however, we do get 0/0, so we can apply L'Hopital's rule in that instance. Derivative of the top, derivative of the bottom, plug in 1. Now, what if after this step, we still get 0/0? Yeah, we can do it. Yep, derivative again. Take the derivative of this, take the derivative of that, reevaluate, and that should get you down to a real number. So each time you get 0/0, you can do L'Hopital's rule once. But as soon as you do L'Hopital's rule once, that you're following it up with direct substitution. All right, any questions with these minor topics here? Linear approximation and L'Hopital's rule. All right, number 4, cylinder. Okay, what's nice about cylinder? Radius is what? Constant. Okay, and just be careful. You may have some information that you don't need from this problem, so just be aware of that. That you only, there's no need for similar triangles. We want to just be aware that sometimes we get thrown off course with cylinders because we see all these information and we feel like we have to use it, and so I think sometimes students want to gravitate towards similar triangles because they're like, well, maybe I need to use, that 20, that 16, that height, and in the height of the water level. So just know that with cylinders, as soon as you get that radius to be replaced with a number, you're ready to find the derivative. That's all you need to get your derivative up and running. And you don't need as much information as you need as for cones. Okay, what's the radius that we're going to use? Good, 6. So put that 6 in for R. You should be ready to build your derivative and solve for your dH dt. So we don't need the height of the container. We don't need to know that the water has a height of 3 centimeters. It's not going to be used at all. So we know our radius is 6, put 6 in for R, get that cleaned up. And as soon as you do that, you're ready to find your derivative. V becomes dv dt, H becomes dH dt. Your dv dt is a -5. And divide that 36 pi over and you're done. All right, number 6, page 6. right, so we have a boat pulled towards a dock by a rope. And the rope is, so here's the boat. The dock is up here. Right, next. So there's our Pythagorean theorem problem. Z is the rope. The rope tied to the boat is pulling that boat closer towards the dock. The rope is hauled in at a rate of 2 feet per second. How fast is the boat approaching the dock when 10 feet of rope are out? Okay, so Pythagorean theorem here, x squared plus y squared equals z squared. It's going to list out all the variables involved. All right, let's go through the question again here. Boat is pulled towards the dock by a rope from the bow through a ring on the dock 6 feet above the bow here. So what can we assign that 6 to be? Y, okay. The rope is hauled in at a rate of 2 feet per second.
dx.
Well, the boat is headed towards the dock, but the rope is, yeah, okay. So any adjustment with dc dt? Negative because, yeah, so that string, that rope is getting smaller, right? That this triangle is getting smaller. Everything is going to be shrinking. dc dt is going to be a negative 2. How fast is the boat approaching the dock? What are we looking for? dx dt. Okay. And the dock, when there's 10 feet of rope out. D. Right? How can I find x? Pythagorean theorem, a squared plus b squared equals c squared. You can also recognize this as a variation of a 3, 4, 5 right triangle. So, but either way, you'll get 8 as x. Are we okay with that? Finding that x. All right, what's dy dt? 0. Why is it 0?
It's not changing.
Right, it's not changing, right? That boat is gonna, furthest is gonna go is here, and that distance from the water to the dock is still gonna remain 6 feet. So that rate of change is gonna be 0. Okay, put everything into your equation and then solve for dx dt. It makes sense that we're getting a negative value for dx dt because as the rope is pulling the boat closer towards the dock, we expect that horizontal x to be decreasing as well. So dx dt should show up as a negative, and it does. All right, part B, at what rate is the area of the triangle changing? So what's the area triangle formula? Yeah, base times height, and the base and height, we want to use what? X and Y. We can go through what to find the derivative. Product rule, okay? So build out your derivative using product rule. And you can put everything from part A into your variables. F prime G plus FG prime. Units of measure, area is square feet, time is seconds, so square feet per second. All right, number 7, cone problem. See how much you can set up on your own. Spend a few minutes, see if you can decide which direction you want to go for number 7. In a few minutes, I'll go through the steps. Right? We're looking for dH dt. So that's a big hint. That means we want our volume equation in terms of height. If we want to keep height in our equation, that means we want to remove r. And if we want to remove r, that's why we want to solve for r so that we can find a replacement for r in terms of h. And then we have to keep reminding ourselves that when they give us that height of the water level, we want to box it off and remind ourselves to not touch that value until after the derivative. We want to hold on to our h variable until the very end. We don't want to lose that h value, h variable too soon. Replace your r variable in terms of h, clean it up, but make sure that you know how far to clean up before you do your derivative. So your fraction needs to come together, your variable has to come together. So we need to be at this space before we even consider our power rule. If we do power rule before this point, it's going to throw you off. So you got to get to this point before you consider your derivative process. Okay, so now derivative, v becomes dv dt, h cubed becomes 3h squared dh dt. We keep that 3 pi over 16. And now we can start plugging in all the values that we have in front of us. Hold on to that pi notation. And in this case, it's going to end up in the denominator. Oh, another common mistake that I see at this stage is so I see students just squaring the h and they forget to square everything inside. So the 3 gets squared, the 4 gets squared, the h gets squared. So just be aware of that. That if you see a parentheses and squared outside, that squared is going to see everything inside the parentheses. Okay, last problem. Let's do the cube and surface area problem on the next page. The formulas are provided for you. Get your derivatives out of the way, and then we can just decide where the pieces fit to get to the variable you're looking for. Okay, so v is x cubed. We find the derivative, dv dt becomes 3x squared dx dt. S becomes ds dt. 6x squared is 12x dx dt. The volume of cube is decreasing at a rate of 10 cubic meters per hour. We know that's talking about volume decreasing, so that's -10 for dv dt. How fast is the surface area decreasing? We're looking for ds dt because we see there's a movement with surface area when the surface area is 54 square meters. All right, so everything that we need is in front of us. We just have to substitute and work our way to our solution. So ds dt is our ultimate goal. We need x and we need dx dt. We don't have these given to us initially, but we have something that's related. The s can plug in to help us solve for x. And once we solve for x, we can use the dv dt to help us get to dx dt. Once we get the two related variables that we need, then we can plug these in and find our ds. So I'm using my surface area equation to help me get to my x, which I'm going to need later. Then I'm shifting over to that dv over dt equation to help me get to the dx dt variable that I need. And then I should have everything that I need to get to the last variable that I'm looking for. And our units of measure, surface area is square meters, time is hours, so square meters per hour. Okay, no homework tonight. I'm just gonna check pages 1 and 2 tomorrow, which I think we all did and finish in class. And tomorrow we'll work on the next 2 pages. It's nice that we've seen pretty much all the varieties of problems. The only one that we haven't gotten to today is the shadow problem. We'll do that tomorrow, but we're just gonna cycle through these types of problems up until next Tuesday's quiz. Oh, I have your test graded. I'll put them in the grade book tonight.
Really good at it? Yeah, what was that?
They're pretty good.
Thanks. Like B average, A average.
At least a high B, if not higher. It's good. Really good.
I was really sitting there.
Oh my gosh.
How about like a 90?
The guy took it like 70 to a 95.
Yeah, you got. You almost, yeah.
Thanks, guys.
Okay. Thank you.
Bye. Have a great day.
Thank you.
Thanks, guys. Have a great day.
Thank you.
Bye. Have a good day.
Yeah.